the review. Yeah, JJ. I believe so, yes. Of course. So you mean 1A? Sure. Miss Anderson. Of course. All right. So, Ben, if I'm looking at A, which side would you want to start with? The left or the right? Well, to me it doesn't really matter. When I look at this, I see there's just one thing on either side. On the left side, there's just one fraction. And on the right side, there's one product. To me, it seems the same. So I don't think it really matters. So I'm really just kind of asking you which side you'd want to start with. No, there's not like a right or wrong answer most of the time for these. There's definitely like an easier answer for some of them. This is not one of those, though. Okay. So when I look at the left-hand side, what part of the left-hand side are we going to probably want to do something to first? The numerator or the denominator? The numerator. Okay. When I look at the numerator, this almost looks like one of the altered Pythagoreans, right? I know that 1 minus cosine squared is 1, or is equal to sine squared, but here I have cosine squared minus 1. The negative signs are opposite. Everybody see that? What can I do to fix that? Let's factor out a negative 1. Everybody happy there? And now I can apply that Pythagorean, right? 1 minus cosine squared is sine squared. And I'm just going to drop the negative 1 and just turn it into a minus sign, like that. Is everybody okay there? Now let's look at what we're trying to get to. I notice that my final answer that I'm trying to get to has a sine alpha in it. And I have sine alphas here. So what I'm probably going to do is I'm going to break that apart. And write that sine alpha as, or sine alpha squared as sine alpha times sine alpha. So now I have the sine alpha, and I have the negative sign. Not touching either of those things anymore. I have those two parts of it set. Everybody agree? Okay. So the last thing then is somehow tan alpha needs to be sine alpha over cosine alpha. Is exactly tan alpha, isn't it? That's our identity. I would say as long as you're using just one identity per step, I wouldn't worry about it. As you've noticed here, I haven't included any identities when I did this here with you guys. And when you're just doing like one thing, I don't know that it's necessary to do that. It should be pretty clear to the reader what you did, as long as you're just doing kind of like one thing in a step. If you start doing like, oh, I'm going to do an algebra thing and do these 3 identities and there's my answer. It's like, okay, I need to see like one thing per step if you're going to do something like that, or else you better be making some notation as to like what in God's name you did to do like a bunch of things all at one time. But in general, like, no if you're doing one thing per step. Okay. Benji, you happy with that? Yeah. Not too bad, right? No. Trickiest part was probably taking the negative 1 out in the beginning. Yep. If you didn't see that right away, hard to see the answer at the end, but if you thought to do that, Not so bad. All right. Who's next? Megs. Sure. 2A then, we'll call that. Great. Which side did you want to work on? Okay. So what did you want to do first on the left? Yeah. Yeah, so what Megan noticed is that cosine x minus sine x quantity squared, that's the same thing as cosine x, or minus sine x times cosine x minus sine x. And you can FOIL that out. And now you'll just, hopefully everybody will trust me. I'm not going to write out the FOIL. I'm just going to write out everything, the final answer after I've FOILed and collected like terms and all that mumbo jumbo. And you're free to do that, right? Like, I don't need to see, like, do 4 things and then combine the like terms. You can do that if you want. That's fine. Not a big deal. But if you know what it's going to look like when it FOILs out, like, you can just write the FOILed out thing. Good here. That's what you did. Okay? I see something right away here to do. Yeah, we have a cosine squared and a sine squared, right? That are just positive. They're being added together, basically. What do those turn into? And we're done. Again, everybody okay there? Okay. Who else has some? Sydney? Sure. Mark, you're starting to have your hand up. Were you have a question about part A, or did you have a different one? Okay. All right. So, Sydney, which side did you want to start with? The right? Okay. Did it matter to everyone? Definitely not, right? You get to the same result either way. Okay. So we're going to start with the right-hand side. What do you want to do first? I'll tell you what I would do first. Factor. Yeah. So notice there's a greatest common factor of secant squared. That realization makes life enormously easier if you catch that. If you don't catch that, and similarly, if you decide to work on the right-hand side, you start by taking a tan squared out. If you don't catch that right away, though, this problem can become really a big pain in the butt. Still doable if you don't catch that, but much, 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 much worse. Okay. So, what do I do here? Yeah, secant squared is the same thing as tan squared plus 1. And then secant squared minus 1 is the same thing as tan squared. That's, both of those are using different versions of P3. And then if I just distribute things through, I get tan to the 4th plus 1, or plus tan squared. And we're done. So if you didn't factor that secant squared at the beginning as your very first step, this got pretty messy. Still doable, but you have to do like some pretty crummy foiling and making sure you distribute some negatives, and it gets a little convoluted. Yeah. If you want, we can do it that way. You're happy? Okay. Again, if there's, on any of these, if I do them and you're like, could we have done yada, yada, yada? Please, like, speak up and let me know, and I'll be happy to kind of try it with a different approach to see what it looks like. if that's, you spent some significant time trying to do it a different way and you want to see, like, how close was I? Did I make a mistake in what I had done here before I quit? Kind of thing. I'm happy to do that sort of thing, okay? Who's next? Abby. 2C? Sure. Which side did you want to work on first? You want to work on the right-hand side? Okay. Can I be honest with you real quick? I would have worked on the left, but we can certainly do it still from the right-hand side. So right away I noticed that I have a cosine. I know I got to get cosine to the fifth in my final. So somehow this stuff has to end up becoming cosine to the fourth, right? Everybody agree with that observation? So I'm never going to touch that cosine on the outside. I'm not going to multiply it through. It's just going to chill out there until I can figure out what to do with it. Everybody's good? Okay. All right. Here's the tricky part now. The piece in green looks like a quadratic. You're not convinced? If we say let y equal sine squared x, I'd have 1 minus 2y plus y squared, right? Now it's definitely a quadratic. How would it factor? 1 minus y times 1 minus y. You guys agree with that? So I could rewrite this as 1 minus sine squared x squared times cosine x. Now you see it, right? Yep. 1 minus sine squared is cosine squared. And cosine squared squared is cosine to the fourth. And along with that extra cosine on the outside, we have cosine to the fifth. And we're done. So if I worked on the right-hand side, which is what I said to Abby, like, ooh, that's what I would have done. What I would have done is I would have written this as cosine to the, or cosine squared times cosine squared times cosine. And then, well, I can do that. And when I FOIL, I get it. So in general, like, to me, foiling is usually easier to see than factoring is. You know, sometimes it's not the case, and you see factoring is easier than I see foiling, whatever. But I saw the right-hand, or the left-hand side, and I'm like, I'm just going to break that up into two cosine squareds, turn them into sine squareds, and multiply that out, and it should give me that other part. That's how it has to work. There's no other way to turn cosines into sines, so it seemed easier than trying to sort through the factoring there, which maybe that's clear and obvious, and you look at it and be like, oh, I see what to do with that. Maybe it's not, right? Yeah, so that's looking at the right-hand side, and I'm like, okay, I just multiplied out some two, you know, like just did some foiling to get that. So I just used the left-hand side to find some foiling to do, if that makes any kind of sense. And to me, that seemed easier. It may not have been more obvious, but to me it looked easier to kind of do that than the other way. But that certainly violates the principle of starting on the more complicated side, right? Because nobody's going to argue that the left-hand side is less complicated or more complicated than the, you know, than the right-hand side. But like I said before, when you said this, like, these are just general rules, and it doesn't matter which side you start with. You can always do it. Sometimes it'll be easier to do it than others. But in general, like, more complicated is probably the easier side to start with, but not always. And again, it matters a little bit from the eye of the beholder, like what's obvious or not obvious. I think in either case we'd use 3 steps, unless you count this where I explained how it was factorable, right? If you don't count that, it's what I have 3 steps there and 4 steps there, so it's basically the same thing. All right. Who's next? Somebody else had their hand up. Lindsay. 3C. Love to. Oh, yes, this one. Okay, Lindsay, which side did you want to start with? The left. Mark? Of course. Okay. Lindsay, I'm going to say something right from jump here. I would have done the right. We're going to do the left because that's what you've asked for. If you want afterwards, I can explain to you what I saw on the right-hand side that made that look more appealing to me. Because they really look about the same, right? You have just one fraction either side. But I'll explain to you what I saw on the right to make that side look more appealing. I think it's a little bit easier. Because the first step here on dealing with the left-hand side is the trickiest one. If you did the first step, you're probably going to be okay. What do you think the first step is? I'm turning those 1s into sine squared plus cosine squared. Not an obvious thing to do. But at some point, you're going to need to do just that in order to do this. And I'll explain to you while I'm writing this down why I would think to do that. Here's why. Is because I see this coefficient of 2. The only way I'm getting that is if I'm foiling something out that has like, sine plus cosine or sine minus cosine or something like that. That's the only way I'm going to get that. So I need to end up with some kind of a quadratic here. And the way I'm going to get the squared terms from the quadratic is by using that Pythagorean. Does that make sense now in seeing that? Not an obvious thing to do, though, at all, right? If I look at the numerator now, that's factorable. You basically have like x squared plus 2xy plus y squared, where x is like sine x and y is like cosine x. Maybe I shouldn't have picked x and y since I already have x's in there. Maybe I'll use z's. That's kind of stupid. Now I have 2's and z's in the same problem. My z's look a lot like my 2's. But do you see the factoring now that I point that out? Not obvious, again, to see that right away. So that's going to give me sine x. Well, I'll write it in the other. I'll write cosine x plus sine x squared, because there's really 2 of them. That factors into z plus y times z plus y, in case you were wondering. When I combine like terms in the denominator, I get minus sine squared. Okay with that, Lindsay? What do you see in the denominator? It's not an addition problem, so it's not 1. Yeah, it's a difference of 2 squares there, so I factor again. And again, keeping in mind where you're going should give you an indication that, like, ooh, I don't want to turn that into 1, right? And then those reduce, and you're at the end. That's kind of nasty, right? Yeah, again, if you hadn't thought to turn those 1's into sine squared plus cosine squared, rough. to get to the answer there. I don't know that there's a way to do that without having done that. Or if there was, it would have been something even trickier than that. Yeah, I'm not sure that there would have been. So if I worked the other side, it's really quite lovely. So remember how we talked about this coefficient of 2 here on the sine x, cosine x being likely the result of some kind of factoring or foiling? That's what I'm going to take advantage of here. And I'm going to just multiply the top and bottom by cosine x plus sine x. So when I FOIL that all out, I get cosine squared plus 2 cosine x sine x plus sine squared x over cosine squared x minus sine squared x. If I use the first Pythagorean in the numerator, that fixes my numerator to what I need it to be. Right? Then I just have to worry about the denominator. To do that, I'm just going to turn sine squared into 1 minus cosine squared. And then when I distribute that negative through and combine like terms, I'm going to get 2 cosine squared x and then a negative 1. And that seemed easier to kind of get down, like the downhill ball rolling on that one. Once I did that first step, everything afterwards was pretty obvious in terms of what to do. And here, this was almost a guess, to be honest with you. Like to do, knowing that that's what you're going to multiply the top and bottom by. But I knew it was going to be something with sines and cosines in it, because that was how I was going to make this term here. So it was a little bit tricky there. Okay. Any more from this sheet? I think this was maybe the worst one on here. Megs? 4B? Oh, okay. Which side did you want to work on? You want to work with the left? Good. I want to work with the left also. Okay. So, what do I see? This is what I notice. So I'm going to rewrite that cosine cubed as cosine squared times cosine. So that cosine piece is locked. That's the cosine at the end. Not touching that. Good with that piece so far, Megs? So somehow, sine cubed times cosine squared is going to have to turn into that stuff. Well, seems obvious to me to rewrite cosine squared in terms of sines, since the green part on the right-hand side has all sines in it. So I know that cosine squared is 1 minus sine squared. And then all I need to do is distribute. kind of got it. If you had chosen to work on the right-hand side, not much different. The first step you would have wanted to do on the right-hand side was factor sine cubed from that quantity. And then it should be obvious kind of where to go from there. It's not too much. Not too tricky. At first glance, though, seems bad, right? It's just about making that first algebra choice. Yeah. Michael? Sure. Anybody else on this identities page? Sit. 5C. Okay. What side did you want to work on? Yeah, that's a joke, right? This would be a nightmare trying to work from the right-hand side back. Yeah. You could. It would work. You have to be real clever, though, to see the way there. All right. So, first step, what do you want to do, Sid? Okay. So here's what I would tell you. I have two things on the left-hand side, one thing on the right-hand side. How would I turn two things into one? Add those fractions, make a common denominator. So that common denominator would be sine times 1 plus cosine. So I would have sine squared t plus 1 plus cosine t quantity squared over sine t times 1 plus cosine t. Everybody okay there? We good? Let's FOIL out that 1 plus cosine t. Benji. No, not yet. But what yeah, because it's plus. What I can do, though, I have a sine squared plus cosine squared. That's just going to be 1. Yep. So I have 1 plus 1. That gives me 2. Everybody's good there? What do you notice in the numerator? Greatest common factor. Yeah, everybody see the 2 there? So if I take that 2 out, now what can I do? Ben? Now I can reduce. Everybody see that? So I have 2 times 1 over sine t, which is just, cosecant, as needed. So you good with that? So again, the key there was realizing, like, okay, just got to combine these two things into one. They're fractions, got to just make that common denominator, and usually, like, if you got to that point, should have been able to kind of get there from there, because everything kind of rolled downhill at that point. That was the key there to getting this one moving in the right direction. And then not picking the right-hand side, because why? Right? How would you do it? How would have you done it if you picked the right-hand side? You would have literally had to do like the reverse steps that we did here, and that's a nightmare to come up with, figuring out to do that by yourself. Yes, it would require a lot of insight. Only after you did this direction would it seem obvious what to do going from the other side. No. They're like, oh, I'll just multiply the top and bottom by 1 plus cosine. Maybe you'd think to do that because you're like, oh, it's got to get in the numerator somehow. Like, that's how I'm going to do it, is get it up there. But then, like, taking this 2 and breaking it up into 1 plus 1 and turning the 1, 1 in, yeah. There's a lot of leaps in logic there that would have been tough to see, having not done this direction. So, this is one where decidedly left-hand side was really the only one you were going to realistically be able to work from. Okay, we feel good on the identities, or at least a little bit better. Should we talk about some of the other topics? Cool. Megan, you had one that you wanted to talk about.
Yeah, I'm grade 4 on the homework. Can you just like show how you pick which quadrant?
Yes. I'm just waiting for this to paste. It just takes a minute. I don't know why it takes so long. There it goes. All right. So you wanted to do this using a reference triangle then, is what you're saying. Okay. So I'll start by drawing my picture. So I'm going to start with the fact that cosine is positive. Cosine is positive when x is positive. So we're looking in those two quadrants. And then we're going to look at cotangent is negative. Cotangent is negative where the signs for x and y are different. So it's negative in this quadrant and this quadrant. So my reference triangle I'm going to draw is in the fourth quadrant.
So it's negative when the sine of the x and y are different.
Yeah, because cotangent is x over y. So now I can say that that's our, I'm going to finish it up for everybody else, just in case. So there's my angle theta. Cosine is adjacent over hypotenuse. If I use the Pythagorean theorem then and solve for this side, 16 minus 9 is square root 7. And then that has to be negative because that's the y part and that's in the fourth quadrant. And then I can just use my definition, my right triangle definitions for sine, cosine, tangent, cosecant, cotangent, etc. to find the exact values for those. Everybody's good with that? You know, so for example, like sine is opposite over hypotenuse. And you can continue going from there, right? Just using the right triangle SOHCAHTOA definitions. That's assuming you're doing this as a reference triangle and not using an identity, right? Oops. Do you need to do the other one also, Megs? Okay. All right. Where is secant positive? Same place cosine is positive, right? So wherever the x is positive. Then where is sine positive? Where the y's are positive. So those two quadrants. Where's my triangle or my reference triangle going to be at? Q1. So secant is hypotenuse over adjacent. And then if I use the Pythagorean theorem, that's going to be square root of 24 or 2 root 6. And then you can apply SOHCAHTOA to finish that out, right? Why do we know that 2 root 6 is positive there? It's in the first quadrant, right? The y-coordinate is positive in the first quadrant, so that up and down one is positive. Okay, Megs, you good with that? That was enough of a refresher. Who else wants to talk about some stuff? Linz! 5 on worksheet 1. Oh, I was not expecting that. Not prepared. The answer is yes, but it'll take me a minute to pull it up here. Oh, excuse me, I got a case of yawns today, guys. So you're looking at this one here, yes? Okay. Ignore the numbering, somehow that's goofed here. Okay, so when I look at this, I see quadratic. So I'm just going to replace those sine x's with y's. Gives me this. How do I solve a quadratic equation? Quadratic formula, or I could try to factor it. Good with that, Lindsay? Do you have a preference? Which one would you rather do? Okay. Notice that for this one, since the leading coefficient is 1, is not 1, excuse me, we're going to have to do the long factoring. So I need two numbers that multiply to give me 2 times 1, the leading coefficient times the constant term, and also add to give me 3, or the null term. What are those two numbers? 1 and 2, yep. So I'm going to replace that 3y with 1y plus 2y. Notice that's still the same thing as 3y, right? I make two groups. From the first group, I can take a greatest common factor of y, leaving with 2y plus 1. From the second group, I take a greatest common factor of 1. So I still have 2y plus 1. Good so far? Okay. I notice there, each of those contain a 2y plus 1. So when I factor that out, I'm left with y plus 1. And now I can apply the zero product property and set each of these equal to 0. To get this. But we weren't solving for y. What are we solving for? X. So let's drop sine x back in there. So x is going to be the sine inverse of negative 1/2. And then x is going to be inverse of negative 1. If I go to the unit circle, sine is equal to negative 1/2 at 7 pi over 6. And then again at 11 pi over 6. And sine is equal to negative 1 at exactly one place, 3 pi over 2. Hold on real quick. Let me double check. And then we want our answers on the interval 4 pi to 6 pi. Or the answers I've given on that interval. No. So we need to find an answer coterminal to these that is on the interval. How am I going to do that? Just going to add 4 pi to each of them. Everybody's okay with why 4 pi? The interval's from 4 pi to 6 pi. If I add 2 pi twice, that'll still coterminal, but now it's in between 4 pi and 6 pi. So if I do that, that's going to be, what's that? I'm so slow right now. 24 pi over 6 is what I'm adding, so that's 31 pi over 6. And then 35 pi over 6. And then this one would be just 8 pi over 2. So those should be my 3 answers I'm looking for. Is that okay, Lindsay? Did I motor through anything too fast? Others? Sorry, sometimes I just get rocking on stuff and just like get excited. If I go too fast, please stop me. Okay? You're entitled to do that. If you don't understand something, or I went too fast, or buzzed through some detail, or whatever, please stop me and be like, so you did something back there? Like, what happened again? Yeah. So this would be an example of that kind of problem. And a reasonably fair example. Like, that was hard, but not... Really, the factoring was the hard part of it, right? The solving part was not too bad. Sure. Is that far enough? More? That's good. Okay. Anyone else? We still have, like, what, 15 minutes here. I'm happy to do some more. You guys have a bunch of time left. Yes, Sabrina. I'm not Sabrina. Now it's stuck in my head, and that's all I can think of. It's Miss Fitzgerald. Let's go with that. 6 from worksheet 1, of course. My apologies. So that's this one. Eb? Of course. Miguel, you good with what I... Okay. All right. So, first thing I'm going to do is factor this. I notice there's the greatest common factor of sine x I can pull off. I can then apply the zero product property. Here I'm going to add 2 and then take the sine inverse. So if I go to the unit circle, the y-coordinate is equal to 0 at 2 places, 0 and pi. If I go to the unit circle, there's no places where sine is equal to 2. Well, maybe it's not a unit circle value, and maybe it's something I'd have to use my calculator to do. Nope, not that either, because what's the domain for sine inverse? It's on your identity sheets. It's -1 to +1. That's you're saying the range, Lindsay. But that's correct. The range, as you said, was correct. We're asking for the domain. The domain is -1 to +1. 2 is outside of that domain. Can we take the sine inverse of something outside of its domain? That just gives you like a no solution for this part. So we can ignore it. So we only care about these two answers. And then if I want those on the interval from 4 pi to 6 pi, actually I think it was this, I'm just going to add 4 pi to each of these. The one that I have to be careful about, though, is the 0. Because if I only want the 4 pi answer, why don't I also want 6 pi? The interval has a parenthesis on it, right? If that was 4 pi bracket, or bracket 4 pi, comma 6 pi bracket, I'd also want to list 6 pi as an answer here. But that's not the case. So, is that cool? Julia, it finally came back to me after I got the wrong name out of my head. My apologies. Sometimes it just happens. I don't know. It's been one of those days. You ever make a mistake? Happened to me. Never. I'm pretty close to perfect. Maybe tomorrow I'll get there. That's an ongoing joke. I say that every day. 7 and 8. Are you talking from the worksheet?
Yeah, take this one up.
Well, I'd have to look at what they are. They're both reasonable questions. Would you like to do one?
Yeah, maybe 8.
Okay. When I went by and checked, this was the most skipped problem in the homework. Most people said this was like not possible or some nonsense. This is perfectly possible. Notice that what we have here is not cosine x times sine x equals 1. This is cosine of sine x. So I'm going to try to get that x by itself. The first thing I'm going to do that is I'm going to try to cancel out this cosine. How do I cancel this cosine? I take the cosine inverse of both sides. Right? Now normally we don't explicitly like write that step out, but that is what's going on when we have like where we move from like this step to this step, right? We're taking the sine inverse to both sides, and the sine inverse is canceling the sine, leaving just the x. We usually just don't write that part out, but that's what we're doing there. When I go to the unit circle, cosine inverse of 1 happens at exactly one location when cosine is 0. And then I do the same thing. So I do sine inverse of both sides. So sine is 0 at exactly 2 places, 0 and pi. And now I don't remember the interval that we're supposed to solve over, so let me go back and check that really quick. All values, okay. Well, this is easy. I can write this as a single answer. I can just say 0 plus pi k, or really just pi k. That was kind of a tricky one, right? Where you had the two trig functions wrapped inside of the other. If this cosine inverse of 1 was any answer other than 0, what's going to happen here? No solution. Because anything other than 0, you're going to get an answer outside of the domain of sine inverse. Right? The smallest, well, I guess pi over 6 would have been okay. If you got pi over 6, you could have done that, but you would have gotten a non-unit circle answer. I wouldn't mark that wrong. It's still, I mean, it's like if you wrote 2/4 instead of 1/2. I typically wouldn't, unless it says expressly, like write as a reduced fraction, I wouldn't mark that wrong because it's still the correct answer. You know what I mean? So I just do that and make a point of doing it because if you're taking a multiple choice test, they would not list it as two separate answers. They would for sure list that as a single answer. So I wanted to make sure you're kind of familiar with, you've seen that kind of thing before. Because I think stuff like that creeps onto the ACT every once in a while. I think I've seen it there before. So. But I'm usually pretty flexible on that kind of thing, right? You guys have seen my grading on your tests in the past, and it's usually pretty lenient on stuff like that, where it's like the right answer, but not maybe reduced the way I expect you to, or not reduced at all. Usually don't care about that kind of stuff. Unless the context of the problem really kind of requires it. Anybody else? Got time for at least one more if anybody's got one that's been bothering them. Or you can just relax for the last little bit. Either is fine. Okay. We're all checked out. That's cool with me.